50,000 American homes are still wired with a metal that the industry quietly stopped trusting in 1974, and nobody came back to fix most of them. Here's the number that matters. A connection made with aluminum wire is 55 times more likely to reach fire hazard temperatures than the same connection made with copper. Not twice, not 5 times, 55. That statistic comes from a Consumer Product Safety Commission study, and it's the reason this topic isn't nostalgia. It's live risk sitting behind drywall in roughly 2 million houses built between 1965 and 1973. So here's what you'll actually understand by the end of this. Why aluminum fails at the connection and nowhere else. Why copper doesn't have this problem. Why the fix has existed since the Ford administration. And why insurance companies are still pricing this risk into premiums 50 years later. Start with the metal itself, because the failure isn't random. It's built into the atomic structure. Aluminum has a coefficient of thermal expansion about twice that of copper. Every time current flows through a wire, it heats up, and every time the load stops, it cools down. Copper expands and contracts modestly through that cycle and comes back close to where it started. Aluminum moves much further, and it moves unevenly against the steel screw terminal it's clamped to. That mismatch is the whole story compressed into one sentence. Two metals expanding at different rates, torn apart a fraction of a micron at a time, thousands of times over a house's life. The interesting part is what happens in the gap that mismatch creates. Once the aluminum wire pulls back even slightly from the terminal, a microscopic air gap opens at the connection. Aluminum reacts with oxygen almost instantly, faster than iron, faster than copper, and that exposed surface forms aluminum oxide within seconds of contact with air. Aluminum oxide is a ceramic. It is, for practical purposes, an electrical insulator, roughly 1 billion times more resistive than the metal underneath it. What matters here is that this oxide layer doesn't stay put on the surface the way it does on a piece of raw aluminum siding. On siding, that oxide layer is actually protective. It seals the metal from further corrosion, which is why aluminum doesn't rust the way steel does. But at a connection point under a screw terminal, the oxide keeps growing into the gap created by thermal cycling. And it keeps growing because moisture and oxygen keep reaching newly exposed aluminum every time the joint flexes. Here's the mechanism that turns a chemistry problem into a fire. Ohm's law says power dissipated at a junction equals current squared times resistance. As the oxide layer thickens, resistance at that one connection point climbs, while the resistance everywhere else in the circuit stays normal. Current doesn't care. It keeps flowing through that same 15 or 20 amp circuit at the same amperage. All the extra heat generated by that added resistance concentrates in a spot roughly the size of a screw head. The reason this becomes ignition and not just a warm outlet is a feedback loop, and it's worth sitting with because most explanations skip it. Higher resistance generates heat. Heat accelerates oxidation because oxidation kinetics roughly double for every 10 degrees Celsius rise in temperature. That's the Arrhenius relationship at work. More oxide means more resistance. More resistance means more heat. This isn't a linear decline, it's a runaway loop that can sit stable for years and then accelerate in weeks once it crosses a threshold, which is exactly why these fires have almost no reliable warning signs before they happen. Compare that to copper, because the difference explains why nobody worries about copper wiring the same way. Copper does form copper oxide, but copper's thermal expansion is low enough that the joint rarely loosens in the first place. The mechanical gap that starts the whole oxidation cascade in aluminum simply doesn't open up. Copper also creeps far less under sustained pressure from a screw terminal, a property called cold flow resistance. Aluminum, by contrast, slowly deforms under the constant clamping force of the screw, a phenomenon literally called cold creep, which loosens the joint mechanically even before thermal cycling gets involved. That brings up something worth pausing on before we get to the money. Why did the industry ever switch to aluminum in the first place, if copper is this much more stable? The answer is the copper price spike of 1965. Copper prices roughly doubled in a 2-year window as demand from the Vietnam War effort and global construction competed for supply. Aluminum cost a fraction as much per pound and conducted electricity well enough for residential circuits, so builders switched en masse for cost reasons that had nothing to do with the metallurgy anyone eventually had to reckon with. The part the industry got wrong wasn't the switch to aluminum. It was pairing aluminum wire with devices designed for copper. Early aluminum-era outlets and switches used the same steel screw terminals, the same alloys, the same torque specifications that copper connections used. Nobody re-engineered the connection hardware for a metal with different expansion behavior and different creep behavior. And that mismatch, not the aluminum itself, is what the CPSC's 55 times figure is actually measuring. The fix arrived faster than most people realize, which makes the 50-year persistence of this problem even stranger. By the mid-1970s, manufacturers developed the COAALR-rated switches and outlets, devices with connection hardware specifically designed to handle aluminum's expansion and creep, often using a different terminal alloy and a spring-loaded design that maintains clamping pressure even as the metal deforms. Retrofit options followed, the Alumicon connector and the Copalum crimp system, both of which physically join aluminum wire to a short copper pigtail inside a sealed connector, moving the failure-prone junction to a device engineered to prevent oxidation entirely. So the mid-video question is this: if the fix has existed since the Ford administration, why are 2 million homes still running on the original 1970s connections? The answer is economics, and it's colder than the metallurgy. A full panel and wiring replacement in an average home runs $8,000 to $15,000, depending on square footage and whether walls need to be opened. The Copalum retrofit, the gold standard fix that doesn't require rewiring the house, costs $1,500 to $3,000, but requires a licensed electrician with specialized crimping tools that most residential electricians don't own, and few homeowners know to ask for by name. Compare that to a house fire caused by this exact failure mode. $300,000 to $500,000 in direct damage once you include structure, contents, and the temporary housing costs that insurers pay out. The industry has spent decades knowing the fix costs a fraction of the failure, and adoption still sits below where the risk math says it should. Insurance companies did the math the homeowners didn't. Many major insurers still require an inspection disclosure for aluminum-wired homes, and some charge a premium surcharge or deny coverage outright, unless the home has been retrofitted with COAALR devices or Copalum connections. That's not caution for its own sake. It's an actuarial table built on decades of claims. Data showing the same failure mode repeating at the same connection points, in the same era of homes, at a rate that keeps justifying the surcharge 50 years after the wire went into the wall. What ties all of this together is that the failure was never really about aluminum being a bad conductor. It conducts electricity just fine. The failure is a mechanical mismatch between a metal that moves and hardware that was never redesigned to handle the movement, compounded by an oxidation reaction that turns a loosening joint into a heat source that accelerates its own decay. So here's the engineering question worth answering in the comments. For a CO/ALR rated device to actually solve the cold creep problem, what specific mechanical property does its terminal design need that a standard steel screw terminal doesn't have? New teardowns every Monday, Wednesday, and Friday.